nanohub.org.
All right, I'd like to launch into the first topic of the course, which is this concept of a scanning tunneling microscope. Try to describe to you a little bit about the history, how this instrument came into existence, what the motivation for inventing it was. And we have to talk a little bit about quantum tunneling, which is a quantum mechanical concept in the course of this. So, in terms of suggested reading, these articles, I believe, will be included in this reader that we'll distribute at the beginning of the next lecture. So you will not have to go and get this material. But these are some of the early seminal papers in scanning tunneling microscopy. As you can see, they were mostly written in the early 1980s. The review article by Hansma and Tursoff in '87 is a nice summary of a lot of the early work. So we'll try to identify at the beginning of each lecture articles that are useful for you to read. Okay. And again, the PDFs of the lecture will be available on the web, so you'll be able to go back and look at this stuff in more detail if you don't get a chance to write it down right now. So historically, the issue was, I guess the 1970s was known in science as the decade of surface science. There was the emergence of a variety of techniques that would allow you to characterize the surface, the first 2 or 3 nanometers of a surface in great detail. And when I say characterize, I mean chemically and structurally characterize. A lot of the work from 1920 up until 1970 was focused on the bulk properties of materials. The structure, the electronic properties, the optical properties, the thermal transport properties of bulk materials. But as the semiconductor industry started to take off and became an economic engine in the world, it became important to know what exactly was going on at the surface of a metal or of a surface of a semiconductor. And these techniques called X-ray photoelectron spectroscopy, low energy electron diffraction, Auger electron spectroscopy. All these techniques were invented in the 70s to try to answer the question, what occurs right at the surface of a material? So these are known as surface sensitive techniques. And they basically take advantage of the fact that electrons that are ejected from a metal surface can only get into the vacuum if they are ejected within a few nanometers of that surface. So a probe that causes electrons to be ejected, if that probe causes an electron to be ejected a few nanometers deep into the bulk of the material, that electron will never exit into the vacuum. You'll never be able to measure it. So all these techniques that were developed were extremely surface sensitive, right? And they allowed you to characterize that region that I list on this diagram as surface. Okay, really exciting time, right? This saw the rise of synchrotron radiation facilities in the U.S. It emphasized high resolution electron energy analysis. So there was a lot of effort spent on trying to measure electron energies with very high precision, because all that could be deconvoluted and give you information about the chemical structure of a surface, which was good to know. Okay, about 1980, the realization was, well, okay, we've got tools to measure surface sensitive properties, but these tools average the electronic or optical or structural properties of a surface over millimeters, right? So for instance, if you do X-ray photoelectron spectroscopy and you go to a synchrotron, right, you focus high energy X-rays onto your sample. The diameter of that X-ray beam is millimeters. You collect electrons that are ejected from the metal or the semiconductor, but the electrons are ejected over dimensions on the order of millimeters. And yet, devices in semiconductor electronics were shrinking into the micron length scale range, right? And so if you wanted to understand in detail at a micron size level how the surface properties varied, you needed a new tool. That was a general realization for anybody that was involved in surface physics at the time. And the question is, well, how do you do that, right? How do you probe a surface at a sub-micron length scale so that you can tell subtle variations in electronic structure, subtle variations in atomic arrangements, right? Well, one idea, right, is you just take a sharp metal tip, right? If you take a sharp metal tip and you can position that tip at different points on the substrate, well, then maybe by connecting a bias voltage between the tip and the substrate, you can start to measure local IV curves. Okay? And so a lot of people started to use point probes and pushing point probes into surfaces in a controlled way to investigate how, for instance, an oxide layer thickness would vary as a function of position over a surface, right? That was the motivation. Now, what's the classical picture for this, right? Typically, historically, there was a lot of work done with sharp tips positioned in front of plates, and there was a high voltage applied between the tip and the plate. So I indicate that in the top view of this slide, right? The separation between the tip and this plate was about 10 centimeters. And typically you would have to apply a few hundred to a few thousand volts of potential difference between the tip and the plate, right? And when you did that, when you applied that bias voltage, right, an interesting thing happens, right? You actually start to pull electrons from the tip and collect those electrons with this plate, right? Now, this effect was discovered in the early 1900s, and it was a real puzzle, right? Because how can you explain how these electrons get out of the metal tip and are accelerated and then collected by the plate? How can you explain that? Well, the answer to that question involves you or requires you to understand something about the energy states of electrons in metals, okay? And the way you understand this phenomenon, this is called electron emission, right, is that is shown in the middle panel of this slide, right? You represent the tip as a well. It's a quantum well. In this quantum well, there are electrons. The electrons are filled up to a certain level, which is referred to as the Fermi level. And the energy states that are occupied are indicated by that shaded blue region in this diagram. Now, why don't these electrons spill out into the vacuum, right? Like when you take your keys, right? Why don't electrons just fall out of your keys and roll around on the table? Right? This is a metal key, right? There's lots of electrons in there. Why do they stay in that metal? They stay in the metal because there's this barrier, phi, indicated in this middle slide. This barrier phi keeps the electrons confined to the metal, to the bulk of the metal, okay? And that's an important parameter that'll come up in scanning tunneling microscopy, this work function phi. So if you want to plot the allowed energies, let's say, of the electrons in this metal tip, right, what you would find is that starting in the bottom of this well, there are energy states. These energy states are all filled up to this Fermi energy, which is indicated by the transition from blue to white. The Fermi energy is the most energetic electron that can exist in a metal. there's this work function phi, this barrier height phi, that prevents electrons from jumping into, let's say, the vacuum. And then, in terms of an energy diagram, if you go higher than, let's say, the vacuum level, you pick up classical physics, right? So electrons with energies greater than phi in this diagram can be described classically. Newton's laws of motion, F equals ma. It's classical regime. If you're below this barrier phi, that's a quantum regime. The electrons are bound in a well. Different physics applies. Okay? You can draw a similar diagram on the far right to characterize, let's say, the metallic plate. That high voltage plate is made of a metal. And it also has electrons, and the electrons in that metal are confined to a well. And the electrons in that metal plate can't come out because there's another barrier, work function barrier phi on the right. Okay? And so the classical picture of this tip suspended above a metal plate, separated by a few centimeters, is indicated in the middle panel. In this middle panel, there's no high voltage applied to the plate. The electrons are stuck either in the metal plate or the tip. They can't go back and forth. Now, what we understand is that if you apply a bias voltage between the plate and the tip, then this picture changes. Okay? And the way it changes is the normally flat barrier that's a few centimeters in physical extent, that normally flat barrier now acquires a finite slope to it. And I've tried to indicate that in the bottom panel of this slide, right? As you increase the voltage between this high voltage plate and the tip, the slope of that barrier, right, continues to increase. I've tried to indicate that here. And what you end up with is you finally end up with a situation where these electrons in this tip see a barrier of finite width, right, before they can become classical, right? So if, again, electrons above that solid line, there are classical electrons, F equals ma applies. If you're below this solid line, classically, you can't even talk about an electron beam at that position, right? That's forbidden. You're not allowed to be there. Can't have electrons with those energies. But experimentally, we see that if we put a voltage between the plate and the tip, electrons come out, right? That's experimentally observed, right? So somehow, electrons must make a transition from the well on the left. They're collected by the plate on the right, and they must make a transition by what we call tunneling through this barrier of finite width. So this is quantum tunneling. This was one of the big problems in physics in the early 1910s, trying to explain how electrons can get from the tip to the substrate, properly incorporating all this physics that I've tried to describe in a very hand-waving fashion. Okay? So, how do you think about the problem? Well, a fundamental breakthrough comes along in 1923. This French guy, de Broglie, says, oh, things like electrons can behave as waves, right? This is a very revolutionary hypothesis at the time. Wasn't clear it was true, right? And what de Broglie says is that, you know, we know light is an electromagnetic wave. It has a wavelength. It has a velocity. One of the characteristics of waves is that they can interfere destructively and constructively with one another. You can't do that with particles, right? You take two particles, you try to put two particles at the same point in space, what happens is they scatter, right? They bounce off of each other. But if you take two waves and try to superimpose the two waves at the same point in space, turns out you can do that. You get constructive and destructive interference, okay? So de Broglie's thinking, and he says, well, why can't matter exhibit wave-like characteristics, right? And the question then becomes, well, what would be the wavelength of this matter wave that he was hypothesizing? So he writes down this famous equation. He says that the Broglie wavelength of a particle is Planck's constant h divided by the momentum of that particle, right? And so the momentum is just the mass times the velocity, classically, right? So you have this very clever idea that a particle of mass m can have a wavelength associated with it. Well, that's very revolutionary, right? Most people discounted it, but people started to do other people started to do experiments to see if it was true or not. It turns out it is true, right? It is true, and it allows you to explain that electron emission effect that we described in the previous slide. And I'll try to summarize how that all comes down. Right? The thing that you want to remember, if you just look at the right-hand part of this slide, right, is that particles exhibit this wave-particle duality. This is a fundamental tenet of quantum physics, right? And so then the question becomes, how do you decide whether the particle is going to behave as a particle or as a wave? So let's be specific. Let's talk about an electron. How do you know in advance whether an electron is going to behave as a particle or a wave? And what we now know, looking back, is that it depends on how tightly confined the particle is, right? So for instance, if you just look at the right-hand side of this slide, right, if you put a particle of mass m, let's say it's an electron, mass m, you put that in a box, and if the box has a dimension d, right, and if you calculate the de Broglie wavelength lambda given by this equation, if that wavelength is much, much smaller than the dimensions of the box, then the particle behaves as a particle, F equals ma, right? You got classical motion. All right? But if you now let that particle interact with a system where the characteristic spacing between things in the system is d, right? So this is supposed to be a group of atoms, and the spacing between those atoms is now specified by this parameter d. If this parameter d happens to be comparable to this de Broglie wavelength defined in this way, then the particle will exhibit wave-like characteristics and will exhibit interference, constructive interference effects, right? For instance, is one example. Okay? So this is referred to as the dual character of particles. It's one of the fundamental dilemmas that quantum physics had to sort out. And looking back, this is a real simple way to remember whether you're going to behave, whether particles can behave as a wave or as an actual point mass, right? This depends on the size of the thing that it's interacting with. So what we like to say is if you confine an electron to a very small region in space, it behaves like a wave. If you put that same electron in a big box and let it bounce around, then it behaves as a particle, right? That's the way to keep it straight. And by the way, I just say light's got the same problem. It's got this same duality, right? This is not just specific to particles, right? It turns out light can behave as a ray or as a wave, depending on the size of the thing that the light interacts with. Okay? So the question becomes 1923, this is de Broglie's hypothesis, right? These things are called matter waves because it's a combination of wave-like behavior with matter, right? So the question is, if particles behave like waves, then what is the equation of motion of these waves, right? How do these waves move with position with time, right? So if de Broglie's hypothesis is really true, what are the consequences of that? And that question was finally answered in 1926 by Schrödinger when he developed this Schrödinger wave equation, which has basically laid the foundation for all modern physics that we work on today, right? This is probably the most important development in the history of science because it allows you to understand in great detail the atomic structure of electrons when they're confined to atoms, right? Now, last year I tried to derive this Schrödinger wave equation in one lecture, which is very difficult to do, right? This year I've abandoned that attempt, and I'm just going to tell you a few things because I don't think most of you care about scanning tunneling microscopes. But if you want to understand how a scanning tunneling microscope works, you got to understand Schrödinger's wave equation. I will tell you that this wave equation cannot be derived rigorously, right? It's a bunch of hypotheses that are logically driven, right? And the virtue of the wave equation is that it makes predictions that match experimental results. If Schrödinger's equation did not reproduce any experimental data, we wouldn't be up here talking about it today, right? So just like Newton's law, F equals ma, that's not that's not derived, right? That is like posited. It's this is how force and acceleration are connected. And then you go and you use it and you find out, oh, by the way, it explains a lot of data, right? Same thing with Schrödinger's equation. Schrödinger's equation solves a large number of non-relativistic problems in atomic physics. So it allows you to predict the energy spectra of all the electrons and all the atoms, right? It is a non-relativistic equation. So if your electrons start to acquire relative velocities comparable to the speed of light, Schrödinger's equation has to be modified. And most importantly, this Schrödinger equation describes something called a wave field of a particle. It's called a matter wave, right? And the matter wave is, of course, an attempt to describe this thing that de Broglie came up with, right? This idea that something with a mass actually has a wavelength, right? And so this matter wave, we have to give it a symbol. And the symbol that's found in all the textbooks is this capital psi. So psi is called the wave function. Describes how this particle moves in space. So how much more time do I actually have? So I got 20 more minutes? Okay. All right. So the fundamental operational definition of quantum mechanics is that there is an operator, right? This operator is referred to as a Hamilton operator. It's given the symbol capital H. And what Schrödinger said is this Hamiltonian has the form h bar squared over 2m. So h bar is Planck's constant h divided by 2 pi. I don't know if you're in physics, everyone knows that definition, but if you're not in physics, you may not know it. H is Planck's constant, right? So, Schrödinger says this operator operates on this wave function psi. This wave function psi describes this matter wave. And this equation, given by this operator del squared, U of R is an interaction potential, right? So it's a function. We won't specify it in any great detail. We'll do a simple problem in a few minutes, right? But U of R basically tells how the particle of mass m interacts with its environment, right? The first term, h bar squared over 2m times del squared, right? That tells you what the kinetic energy of this matter wave is. And so this Hamiltonian basically says you take the kinetic energy plus how that matter wave interacts with its environment, that's specified by U, right? And if you can then solve this equation, h psi equals E psi, that's the simple form of Schrödinger's equation, you're then allowed to solve for the energies, the allowed energies that an electron could have. Okay? So, in 5 minutes or less, that's Schrödinger's wave equation, H psi equals E psi, where H is defined as that box at the top of the page. And if you study quantum mechanics in the physics class, you'll spend the whole semester investigating different U's, different values for U, to describe different situations for an electron. You'll solve that differential equation in great detail, and you'll have a whole notebook full of equations for wave function psi, right? At the end of the semester, that's what you do. You learn how to work through this stuff and get these wave functions, because these wave functions then carry all the information about how this matter wave moves both in space and time. Right? One of the interesting consequences of this matter wave is that because the particle has a wavelength, you cannot specify precisely where the particle is located anymore. Right? If the particle is a point mass, in principle, if you spend enough time and effort, you can identify where that particle is. You can track its trajectory in space. But now if the particle is represented by a wave, the wave is delocalized over a region of space. And so you can't really pinpoint precisely where that particle is because it's got this wave-like characteristic. So you find out that the interpretation of this matter wave is this is a probability amplitude, right? This probability amplitude, if you take it, multiply it by its complex conjugate, and evaluate that product, psi star, at a particular point in space, R, that tells you the probability that the electron will be at that particular point. Right? Because the electron is delocalized, it now doesn't have well-defined trajectories. It has probability that it's going to go this way, probability it's going to follow this path. It's got probability that it's going to be a certain point in space. So this psi star is interpreted as in terms of the probability that the electron will have to be at a particular point in space. And then the other interesting consequence of quantum mechanics is this concept of an expectation value, right? So the expectation that the particle will be at a particular point x, right, is defined in terms of this integral, where x is now a quantity that's sandwiched between these wave functions, psi star and psi, right? So this expectation value could be the expectation value for the momentum, the position, the energy, the angular momentum, right? All the quantities that we define in classical physics, there's an analogous definition for the expectation value of that quantity in quantum physics. And the way you evaluate that expectation value is by evaluating this integral, right? So these are a few of the consequences that quantum mechanics, that follows from a systematic study of this thing called quantum mechanics, which again was devised to explain how these matter waves move through space and time as it interacts with its environment, right? The interaction with the environment has to be specified by U. So this is a very high level view, right? We're not getting into the specifics or into any details. Okay, now why am I telling you all this? Well, I want to go back to the same problem we had, right? About how these electrons get out of this metal, right? When they're confined in the metal by this work function barrier phi. I want to come back to that. Right? Turns out quantum mechanics allowed that problem to be understood in great detail. Right? Two guys by the name of Fowler and Nordheim took quantum mechanics, and then in the late 1920s, they developed this Fowler-Nordheim theory that described how these electrons can actually move away from a metal tip, strike this metal plate when there's a bias voltage applied between the tip and the plate. Big breakthrough. The way they did it is they said, oh, well, we're going to take the electrons, we're going to treat the electrons now as these matter waves, psi. So the electrons will now no longer be described by a point mass. They're going to be described by a wave function. This wave function is going to have a certain characteristic wavelength associated with it. Right? What is the form of the wave function? Well, you got to solve Schrödinger's equation. You got to go back and work it out, right? They did that. If you go look at their original papers, they worked out solutions for wave functions for the shape of a barrier that I've got drawn in this diagram, right? Now, the important thing about this barrier is there's a surface barrier associated with it, right? Originally the barrier was this big, flat, square, like rectangular object. This rectangular barrier confined the electrons between the metal, right? The electrons in the metal tip were confined in one region. The electrons in the metal plate were confined in another. There was a big square rectangular barrier that kept them from mixing. But now when you put a voltage between the tip and the plate, the barrier gets deformed, as I've got indicated here. It's got this parabolic-like shape associated with it. The barrier acquires a finite width, and lo and behold, you can solve Schrödinger's equation for all points along the x-axis. And when you solve Schrödinger's equation for all points along the x-axis, you get a wave function that's indicated by this squiggly-looking curve that I've got drawn on this diagram. And what these waves can do, the new physics that these waves can do, is they can tunnel through that barrier. They can penetrate the barrier and come out the other side. Even though classically, right, you'll never get a particle with mass m to move inside that barrier. Right? Classically, if an electron of mass m would strike that barrier, it would be reflected. Right? 100% of the time it would be reflected. But when you allow this possibility that electrons can be described by these wave functions can now penetrate through the barrier. There's a certain probability, that's the way we talk about it, there's a certain probability that the electron can move through the barrier and emerge on the far side. When it emerges from on the far side, it's a classical electron. It's got an energy that you could measure. It's got a velocity that you can measure. It's got a mass that you can measure. When the electrons are on the far left, they have a mass, they have a velocity. When the electrons are in that barrier region, they're acting like a wave, right? It's one of the mysteries of quantum mechanics. Schrödinger's equation takes this all into account and allows you to predict the probability now that an electron can go from the left to the right through that tunnel barrier, surface barrier. Notice that the surface barrier, for this to work, the surface barrier is small. It's about 3 nanometers or so in width. Right? That's an important parameter for you to keep in mind. Right? As the width of this surface barrier gets larger and larger, the probability that you tunnel through it gets smaller and smaller. Orders of magnitude smaller. Right? Orders of magnitude smaller. So that's the basic physics, right? This is the physics of field emission. Right? And why is it relevant? Well, it's relevant because if you want to probe locally the surface properties of a metal surface, what you want to do is you want to bring this tip, which was, let's say, centimeters away from a metal surface, semiconductor surface. You want to bring that tip very close. And in the process of bringing it very close, you hope you're going to start to get information about the local properties, local electronic properties of the metal surface. Right now, so then you have to start to think, well, what's going to happen if I do that? Right? If I bring this tip close, well, right? You're going to have a tip, which is schematically represented by that block on the left. You're going to have a substrate, which is schematically represented by the block on the right. There's going to be a vacuum gap between them. That vacuum gap is going to be on the order of a nanometer in width, right? How do you describe that situation? Well, you go to an energy diagram, which is very similar to the energy diagram that we discussed in some detail already. right? There's this work function barrier phi that holds the electrons in the tip or in the substrate. All the electrons up to a specific energy E sub f are filled, right? But now this barrier, right? This square barrier, in this discussion, this is a square barrier. This is an approximation to the real situation, right? The square barrier is easy to solve analytically. That's why we use it. But who knows what the real barrier is between a tip and the substrate, what the shape of that barrier is. Right? You can't go to Kmart and buy a meter that measures that, right? You know there's going to be a barrier, you just don't know its shape. So let's think about this square barrier in more detail, right? And it turns out, again, using this Schrodinger's equation, you can solve for the wave functions to the left of the barrier, to the right of the barrier, in the middle of the barrier. And these solutions are called psi 1, psi 2, and psi 3, right? And the solutions involve complex notation. These e to the ikz's, right, represent the wave functions of the electrons to the left of the barrier. They represent the wave functions to the right of the barrier. And then inside the barrier, right, the wave function has to change. It can no longer be complex, right? It changes to just simple exponentials with respect to z, right? This parameter u that I told you was in Schrodinger's equation that describes how the electron interacts with the environment. This parameter u in this particular problem has a very simple form to it. U is 0 to the left of the barrier, U is 0 to the right of the barrier, and the barrier itself is specified by a height which is V naught. Constant, right? Constant value. So, you can solve this problem with Schrodinger's equation. You can get detailed solutions for the wave function psi, right? That's not part of the course, right? But what you can do is you can define a probability current, J, that flows, right? This is detailed background stuff. It tells you, if you're into quantum mechanics, it tells you how you would define this probability current J. It involves evaluating the expectation value of the velocity of the electron. When you evaluate expectation values, you have to go back to this formula, which says you take the parameter that you're interested in this case, it would be the change in the position with respect to time. You have to sandwich that between the wave function psi star psi. You have to integrate overall space. When you do that, the bottom line is, after a couple pages of arithmetic, you get a very simple expression for the probability current that flows through that barrier, right? And if you evaluate that probability current, what you can do is you can eventually calculate the transmission probability for an electron to go through that barrier. And this is the important parameter that I want to get to. This transmission, or this is the important result of the lecture. This transmission probability is non-zero. Classically, the transmission probability would be 0 if the energy of the electron state is lower than the height of the barrier, V0. But quantum mechanically, you have a probability that the electron will tunnel right through the barrier. The detailed form of that probability is given in this formula. And if you make the further assumption that this parameter alpha times the width of the barrier is much, much greater than 1, that just basically means you got a wide barrier. If your barrier is very wide, then you can reduce that hyperbolic sinh function into an exponential. And you get this real simple result, that the transmission probability is equal to a bunch of constants that are related to the problem, times this e to the minus 2 alpha d. And alpha is a decay constant, and for typical barriers, it's a number. It's on the order of 10 to 15 inverse nanometers, right? You can evaluate that. I think there'll be a homework problem where you can put numbers in and you'll be able to convince yourself that this is a reasonable range of alpha, okay? So this is the result we're after, right? We don't spend a lot of time in class calculating these transmission coefficients. If you got the homework problems from last night, there's a couple of simple problems just to give you some experience calculating transmission probabilities. There are many websites available where you can go and you can sharpen your intuition about transmission probabilities. So this website at the University of Colorado is one I use a lot. I give the web address. You can go and you can specify barriers at different heights and widths, and calculation of transmission is performed for you automatically. So that's an option if you want to learn more about this quantum transmission. If you want to learn more about barrier penetration, there are websites available. This is one I like very much. It's this hyperphysics website because it allows you to see how all these topics are interconnected. So if you go to this particular website, you'll find a very nice discussion of barrier penetration, and it summarizes in more detail a lot of the issues that I'm discussing here today. In real life, the situation is always more complicated, right? This is the simplest model you can imagine, right? An electron hitting this barrier, penetrating to the other side. But in reality, the tip, so this let's say represents the tip, this represents the substrate. Right? In reality, the tip and substrate are made up of atoms, and the question then becomes, how is this picture modified? And the answer to that question is that taking into account the atoms, the individual atoms that make up the tip and the substrate, that introduces a rather complicated potential function, which is indicated by these sharp, deep wells in this diagram. Those sharp, deep wells represent the location of atoms in a metal, and they indicate that an electron is strongly attracted to those atomic cores. And so if you want to solve this problem more realistically, you have to take into account these atomic cores. And how to do that is I think, beyond the scope of this course. The important thing is that you have to calculate wave functions that satisfy Schrödinger's equation in the presence of that more complicated potential. And the solutions to that Schrödinger's equation, the wave functions that satisfy Schrödinger's equation, will have a certain value at psi at z equal to 0. So if this is our z-axis, right? And we modify this problem so that we now incorporate these atomic core potentials, right? The net effect is that there will be a wave function at this point which has a specific value, right? And the probability that we find an electron at that point is proportional to the square of that wave function. That's one of the rules of quantum mechanics, right? So how does this wave function then vary as you move out through this tunnel barrier? Well, it turns out it varies exponentially, right? So if I know the wave function at z equal to 0 by some very complicated calculation, right? I can calculate what the value of the wave function is, let's say at z equal to d, by just saying that the wave function decays exponentially in the barrier region. So that's this e to the minus alpha z. This parameter alpha is exactly the same parameter that we developed when we were discussing transmission through the simple square barrier. Okay, and the definition for alpha is indicated on this slide. So the probability that we will find this electron with this energy E at this point D is the square of the wave function at z equal to 0. That's the probability that it's here, times this e to the minus 2 alpha d parameter that's circled in this slide, right? So all we're saying is that the probability that the electron gets from here to here decays exponentially with this e to the minus 2 alpha d factor. And the new thing that these atomic cores introduce is that the probability that you find an electron at some energy here at z equal to 0, that probability is a function of all the details of these atomic core potentials, right? So in a nutshell, that's how you go from a simple square barrier model that everybody solves in an introductory quantum mechanics course to a realistic model for electrons going from a tip to a substrate, where you include the tip atoms and the substrate atoms, right? It then follows that the tunnel current that flows, if the tip is now biased, let's say the tip voltage is raised positive with respect to the substrate by a voltage delta V, then the tunnel current that flows is going to be proportional to to the electrons in that shaded region in this graph, right, times the probability that they get through that barrier. Okay? And so the current is proportional to the probability that the electrons in the shaded region get to Z equal to D, and the probability that the electrons get from Z equal to 0 to Z equal to D is just this wave function psi of 0, evaluated at Z equal to 0, that quantity squared, times this attenuation coefficient e to the minus 2 alpha D, right? And now we have to take into account the fact that there is a range of energies in that shaded region that can tunnel from the left to the right of the barrier, right? That range of energies requires us to put a summation in front of that wave function squared. So if you look at that summation, right, we're summing all the states in that shaded region of the top graph. We're going from EF minus E delta V, where delta V is the voltage applied between the tip and the substrate, all the way up to the Fermi energy of the metal on the left, right? And this more formal definition of tunnel current for a realistic system, that allows us to define something called the local density of states. Because it's not at all obvious that all the electron states for all energies, right, are uniformly occupied now. The fact that these atomic cores are introduced into the problem means that there could be energy gaps or modulations in the density of electron states, right? That's the price you pay when you introduce the atomic cores, right? And in fact, these atomic cores, right, allow you to understand why some materials are metallic and other metals are semiconducting, because when the details of these cores are put in to this problem, you'll find out there are regions in energy that just aren't allowed, right? Now, there's a homework problem to help illustrate that feature a little bit more in detail, right? So that's the second homework problem. So this local density of states has got to be introduced to account for these complications. And the bottom line, okay, the bottom line is indicated in the last line of this slide, that the current between the tip and the substrate is now directly proportional to this density of states times this e to the minus 2 alpha D factor, which is the attenuation through the barrier. And it's linearly proportional to the voltage applied, at least for small voltages, right? When the voltages get large, then there's complications due to the fact that the barrier gets distorted. But for small voltages, to a very good approximation, you should see a current that's linear in voltage and proportional to this local density of states. Right? So that's the complication. I have to mention that it's just because the simple square barrier is like the toy model for tunneling. It doesn't really apply to any real system, but once you understand how the toy model works, then maybe you can appreciate the complication that's introduced when these atomic cores have to be included in the problem, right? So the other thing I have to tell you is, without going into a lot of detail, is that there are theoretical physicists around the world who calculate these local density of states for different systems, right? So you can go to the literature, and for almost any type of metal or semiconductor surface of different compositions of atoms, right, there are local density of states calculations that have been performed. Right, these local density of states calculations involve solving Schrödinger's equation for the particular geometry of the of the material under consideration. So you got to know the crystal structure and you got to know the atoms that comprise that material. You put that into a Schrodinger's equation calculation, you can get wave functions. If you get wave functions, you can square those wave functions and evaluate them at the surface of the metal at z equal to 0. That gives you a density, a local density of states. Right? Tells you how many electrons there are at a particular energy at z equal to 0. And that's what you need to know if you want to calculate this tunnel current. All right, so I just show you various papers that I picked out of the literature. Right, this one is particularly nice, right, because it shows you a tungsten tip above a substrate, and then it considers the atomic wave functions of the lead atom on the tungsten tip, right? Different symmetry wave functions for those electrons in that lead atom. And from the different symmetries of those different wave functions, you can then calculate how the density of states of electrons from that lead atom of the tip propagate through the tunnel gap between the tip and the substrate. And knowing that, then you're allowed to calculate or estimate the tunnel current that would flow between the tip and the substrate through a barrier which is of width equal to the distance between the lead atom on the tip and the atoms in the substrate. Right? So that all has to be factored into a very detailed discussion of scanning tunneling microscopy. Just a word about typical values, right? The important parameter is this, in determining how quickly the wave functions decay from z equal to 0 to z equal to d. The important parameter is called this wave function phi. This work function phi, right? So on this table, I list different work functions for different metals, right? They're all on the order of 4 to 5 electron volts. I calculate the appropriate attenuation constant alpha. You can see the values of alpha for these metals are on the order of 10 to 15, right? Inverse nanometers. And then I ask the simple question, right? If I get a certain tunnel current when the barrier is this wide, and then I change the width of the barrier by a small amount, let's say 1/10 of a nanometer, right? How much will the tunnel current vary? Well, when I change the width of the barrier by a certain amount, I don't change the local density of states in this region of the problem. That stays fixed. All I do is I just somehow make the barrier a little bit wider. Because this is an exponential decay, because these wave functions decay exponentially through the barrier, right? You would expect the tunnel current to decay exponentially also. And in fact, that's what this calculation shows, and it just shows you that for typical values, right? I pick a work function of 5.09 eV, I pick a value of alpha about 11.5 inverse nanometers. Those numbers are completely consistent with the numbers in the table, right? What you can very easily show is that the tunnel current changes by a factor of 10 if the barrier width is changed by 1/10 of a nanometer. Now, 1/10 of a nanometer is 1 angstrom. Separation between atoms and solids is about 3 angstroms, 0.3 nanometers. So if I just change the width of that barrier by 1/3 the separation between atoms in a solid, the tunnel current is predicted to change by a factor of 10. Okay? Huge variation of tunnel current with gap, right? So, to go back to the original problem of probing a metal surface with a tip, right? The reason this tip geometry is so useful is because it eliminates all kinds of possible mini gaps that might occur between a bulk metal and a bulk tip, right? So if you just imagine cutting breaking a metal rod and using that for a tip, you might get the situation shown in the top part of this slide where because of the roughness involved in breaking the tip, right, there are many small gaps, mini gaps that form between the tip and the substrate. each of those small gaps will contribute a tunnel current. And what you measure experimentally is the sum of all those tunnel currents. So that's a very complicated problem. It's much, much better to be able to form a sharp tip where there's literally one atom at the end of the tip. If you can form that sharp tip somehow, we'll talk about how to do that, then you're limited to a tunnel current between the lead atom and the substrate, right? And that's exactly the situation you want to be in. And then this is the famous paper that was published in late 1981, where it was actually demonstrated that if you bring a sharp tip close to a substrate, you bias the tip with respect to the substrate, the tunnel current, in fact, varies exponentially with distance. Okay, so there's like 4 or 5 data curves on this slide. Each data curve follows a linear behavior on this log plot. So we're plotting log of current versus displacement between the tip and the substrate. And the fact that a straight line occurs is an indication that the tunnel current is varying exponentially with distance. When this paper came out, it was very hard for a lot of us to believe that this sort of control of the tunnel gap could be achieved, right? This was a real major accomplishment, and it really changed the way a lot of us started to think, right? It was a very seminal paper. The idea now becomes, right, if you followed the discussion, right, if the tunnel current varies exponentially with position, right, and if the tunnel current changes by roughly a factor of 10 every time you increase the barrier width by 1/10 of a nanometer, then why not use the tunnel current as a height monitor, right? And why that's a good idea is indicated schematically on this diagram, where I plot what an exponential variation in tunnel current would look like as a function of separation between tip and substrate for these alpha parameters on the order of 10 or 12 inverse nanometers. And you can see that the tunnel current rises up very sharply, right, when you start to get to a tip substrate separation of about 0.6 nanometers. And the idea that the group at IBM Zurich had was we can set that tunnel current, we can measure that tunnel current with reasonably high accuracy. Why don't we control the tunnel current by constantly adjusting the distance between the tip and the substrate? So you have to imagine there's a little machine inside the equipment that constantly adjusts this separation. If this separation be constantly adjusted in a precise way, then maybe we can control the tunnel current to, let's say, a set point tunnel current of about 1 nanoamp, right? Then we have a very sensitive height monitor. If something changes on the surface that causes the distance between the tip and the substrate to change by just a 1/10 of a nanometer, that tunnel current is going to change by a factor of 10. So we have an incredibly sensitive way to detect height now of the tip above the substrate. Okay? So that was the idea. And then the idea behind the scanning tunneling microscope is let's just move the tip across the substrate in a controlled way. Now the substrate's going to have all kinds of features on it. The features are going to be atomic scale features. There's going to be step edges, kinks, ledges, whatever the substrate material surface might possess, right? And as we scan the tip over that substrate, if the separation between the tip and the substrate changes even by a small amount, the tunnel current will change. And if we then adjust the tip position to maintain a constant tunnel current, what we're really doing is we're mapping the position of the tip at a certain fixed distance above the substrate as we scan the tip over the substrate. And that is a microscope, right? Because you're now measuring atomic scale features on the substrate by monitoring this tunnel current through a vacuum gap between the tip and the substrate as the tip is rastered systematically over the substrate. Right? So this was the big advance, right? Technically what you do when you measure the current as a function of X and Y, you're measuring for a fixed voltage delta V, you're actually measuring the local density of states across the substrate. So I have to say that because technically that's what you're measuring. But to a very good approximation, if things are reasonably uniform, you're really measuring the height variation along that substrate as the tip is rastered. So that gives rise to the scanning tunneling microscope, the idea behind the scanning tunneling microscope. And that idea followed very quickly after the observation that you could achieve this tunnel gap that was controllable, right? And so I'll end the first lecture by just saying you can imagine using this technology, right, in two ways. One way is to keep the height of the tip constant as it scans across a sample. If you keep that's in the upper panel of this slide. If you keep the tip constant as you scan over the sample, and if the sample has features that go up and down, then the tunnel current will vary exponentially with separation, and you'll get a map in the tunnel current that somehow mimics the geometry of the surface. That's in the top slide, right? Now that's a useful feature, that's a useful way to scan if the substrate is really flat. If the substrate is rough, then it makes much more sense to continually adjust the distance between the tip and the substrate to maintain a constant current. So you have to build a circuit, an electronic circuit that constantly jiggles the tip up and down to maintain a constant tunnel current. And when you achieve that situation, you've got what I show on the bottom panel of this view graph. Right? The tunnel current remains reasonably fixed as you scan across the substrate, but now the path of the probe tip rises and falls to mimic the exact geometry of the substrate underneath. Right? Now the rises and falls that you can see with this technology is better than a tenth of a nanometer. So you're actually imaging sub-angstrom level height changes because of this exponential dependence of the tunnel probability of electrons through this barrier. Okay? So that's the idea behind the scanning tunneling microscope. In the second lecture, we'll talk about some of the experimental ways to achieve this, because some of the techniques that were developed to achieve a scanning tunneling microscope translate directly into an atomic force microscope. So if you want to understand how atomic force microscope works, maybe it's easier to first understand how an STM works. So that's what we'll talk about in the second lecture.